Okay. We're getting to a new chapter today where we focus exclusively on first order ordinary differential equations. So the problem we're going to be considering all chapter long is something of this form, where y prime is some given function f of both t and y. And then there will generally be some sort of initial condition attached to it. And as mentioned, in most cases, depending on the function f, it can be shown that this problem is guaranteed to have a unique solution at every initial point. Now, today, depending on how time passes, we're not really going to be talking about methods for explicitly solving this equation, although that will be a focus in most of the chapter. The focus of today is what can we understand about how the solution behaves, even if we don't have an explicit solution available. So, because that qualitative behavior can be just as useful, maybe even more so, than the actual formula. Because sometimes I can write down a formula for a solution to a differential equation, and some gobbledygook, some nasty function, and you're like, well, what does that mean? That doesn't really tell me anything. Now, if you graph it, that could be informative. But we can have an idea about behavior just bypassing all that, especially for some equations where there's no way of getting a formula just because we have some integral that's too hard to work out, for instance. Okay. So what we can have is called solution curves. This is what the section is called in the book, the textbook, without a solution. Okay. And there are two ways in particular that I'll focus on getting some knowledge about how the solution behaves without actually trying to solve it, which we'll certainly get into on Wednesday. So the first thing we'll look at are called direction fields. Okay. So what is meant by a direction field? How you create one, or generally you would not do one by hand. There's software that can generate direction fields for you. If any of you have MATLAB experience, it's fairly easy to generate from there. Like a direction field that I have in the notes. This is an example of a direction field that was created using MATLAB. No, I will not have you create a direction field on a test. Although one thing that would be a good question on a test, it also is a question in the homework for this section, is if you are given a direction field, understanding what that means. Like on the homework, they give you a differential equation and 4 direction fields, and you're asked to determine which is the correct direction field for that differential equation. So how you generate one, or how to have software do it for you, is at many points in the ty plane. So T1, Y1, T2, Y2, etc., where K has to get pretty big to get a decent picture. You plot a vector that has this direction. So if you think of this as a vector of a t-coordinate and a y-coordinate, if a t-coordinate is 1 and the y-coordinate vector is y prime. So in other words, it is a vector that is pointing in the direction of y prime. Now, how long do you make a vector? That depends on, basically you want to make a vector short enough so that they're not overlapping each other on your plot. So for instance, if you're plotting these vectors at t equals 1, 2, 3, etc., then these vectors should have length less than 1. But it is the direction in which it's pointing that matters. So I'll do an example. Let's see. So dy dt is equal to okay, 9.8 minus 1/5 y. Now, really y would represent velocity, 9.8 is the gravity constant. But since I'm talking about the ty plane, I'm just going to use t and y no matter what the variables actually mean. Okay, so what I can do is, here's my ty plane. Now, one thing I want to point out is I'm labeling my axes, horizontal axis t, vertical axis y, because we're plotting dy dt. T has the same meaning as that x would normally mean. You're accustomed to your xy axes, and rise over run. For some reason, when I was looking at the homework for this section and picking out the problems, it seemed like they were doing it the opposite way, which seemed kind of odd, which is why I'm not changing here, but just keep it in mind which axis is labeled which way before you answer a question. But again, of course, in the homework, something I should have mentioned earlier, you get 5 attempts to get the problems right. Okay, now, so what I can do is I can choose a value of t and y. So you get slope. That is your function f of t and y. So in this case, this is my function f of t and y that gives you the slope. And in this case, it's convenient that the derivative happens to only depend on y. The t value's not going to matter in this case, but generally. So if I plug in, for instance, y equals 0, then what happens is the dy dt is just going to be equal to 9.8. Now, okay. Actually, I'm going to scale here just so I can show you the interesting part of the direction field. All right. So I'm going to move y equals 0 way down here. We're not really going to look at negative values of y. All right. So what will happen is, as I move along the t-axis here, if I want to plot the slope, it's just going to be 9.8. That's going to be pretty steep. Now, I'll put my labels here. Okay. And I use a scale of 10, 60, 50, 40, 30, 20, and 10. And I'm going to use a rather warped scale along it, so it's definitely not going to beat the scale. I'm choosing what makes it easier for me to draw accurately. So what happened is the slope is 9.8, so it's going to be roughly this: a run of 1 and a rise of nearly 10. So I would get something like this. And that's going to be true for each t because the slope only depends on y, not t. All right. Now, if this, dang it, if the axes were to scale, then the actual steepness of these lines would show. Which is that because we have one t unit corresponding to roughly 10 y units, that's why it looks the way it does. Now, suppose I plug in y equals 50. What's going to be dy dt in that case? Minus what? 0.2. Okay. So it's almost horizontal. It's actually going to be pointing very slightly down. So it's going to be something like this. And because the slope only depends on y, not t, once I have this line here, I can just duplicate it going to the right. If I plugged in y equals 49, I'd actually have a slope of 0. So I'd have just horizontal lines. I always find it amusing when a student refers to a line like that. So if I just draw a horizontal line, they call it, it's a straight line. Last time I checked, all lines are straight. So horizontal line in this case. So that's what we'd have at y equals 49. In between, there's going to be gradual progression from something that's this steep to something that isn't steep at all. So for example, if I plug in y equal 20, then the slope is going to be just shy of 6. So it'll be something like that. All right. If I plug in something above, so higher up here, so for example, y equals 60, 9.8 minus 12, so it's minus 2.2. So it's getting a little steeper in a downward direction. Okay. So once you have this direction field filled in, you can actually help see how the solution behaves by connecting the arrows. So if I pick at t equals 0, an initial value, say right here for instance, then I can see that the solution is going to head in this direction, at least for a short time. So once you have a direction field, you have an idea of how solutions behave just from a picture, depending on where the solution begins, what the initial value is. So for example, if I choose initial value down here, the solution is going to increase as t increases. If initial value starts up here, it's going to decrease. If y naught, the initial value, is equal to 49, dy dt is going to be 0. So the solution will be, if I pick it right here, it's going to be a constant. The solution will start at 49 and it'll stay at 49 forever. Just because the slope is not going to depend on t. In fact, the slope's not going to depend on anything. It's always going to be 0. So direction fields give you a way of kind of like eyeballing not just how a solution behaves, but how many different solutions behave. What the initial condition is. You'll see that different initial values can affect the behavior of a solution quite drastically. So the homework is the slope, for instance, doesn't depend on t. Like in this example, then we're going to have this situation like this where these arrows, you have carbon copies of them, move along the t-axis. On a homework, you're given four direction fields, you have to pick which one goes for your differential equation. All right. Okay, so questions about how direction field is made? Yes?
Sorry. Could you go over the one for the 50 and 20, please?
50 and 20. Okay, if I plug in y equal 50, so I have 9.8 minus 10, so minus 0.2 turns out to be the slope. So that's why when I start my arrow at y equal 50, I want a line that has that slope. So I can start at this point. These origin points all have the same y value at the start, y equals 50. So I just draw a line a short distance with slope minus 0.2. Similarly, down here, y equal 20, I have a slope 9.8 minus 4, so positive 5.8. So at each of these points that starts with y equal 20, I want a line that has slope 5.8. Now, on this scale, I have 1 unit in t on this axis, but here I have 10 units in y. So that's why, if I didn't have any axis markings here, and you assumed everything was equal, this would be a line of slope slightly greater than 1/2. But because of the different scales, this is actually a line of slope roughly 6.
Thank you.
Other questions? Now, make sure this is still going. Okay. Now, the fact that there was a particular y value, in this case, y equal to 49, because 49 over 5 is 9.8, that would lead to a slope of 0, and therefore a solution that happens to not change at all, be a constant over time. That's very important to know. If there's any solutions that are called equilibrium solutions, that can help us understand the behavior of a solution for whatever initial value we have. So that takes me to the second way of understanding how a solution behaves without explicitly computing a solution. Okay. Equilibrium points. Or equilibrium solutions. Okay. Now, the differential equation of this form, now before I wrote y prime equals f of ty, here I write only f of y. And that is called an autonomous ODE. So when the time derivative is independent of t, and it was in that example, so the right-hand side depended only on y, not t, so that was an example of an autonomous ODE. So we're going to focus on these. These are much easier to analyze when it comes to computing equilibrium solutions. So if f of y naught for some y naught is equal to 0, then y naught, there are actually several different terms that are given to this case. So it is referred to as an equilibrium solution. Another term for it a fixed point or a stationary point. And the reason why is when this happens, the time derivative becomes 0. So if its derivative is 0, that means the solution is a constant. So the initial value problem that has y prime equals f of y and y of t naught is equal to y naught. So if this value that makes f of y 0 happens to be the initial value, then that's the easiest equation ever to solve. So y of t is just equal to y naught. It starts at that value and it stays at that value forever. First thing we should do, if we are given an autonomous ODE, we want to understand how a solution behaves. It's a good idea to see what the roots of f of y are, if we can. And whether we can or not depends on particular f. Like for instance, if it's a polynomial, and seeing what the zeros are. So that'll give us an idea of which initial values lead to constant solutions. But then we want to see what happens for the other values of y naught that are not equilibrium solutions. Does a solution approach those equilibrium values, or does it diverge away from them? Okay. So, so I need to get some of these notes out of the way that I don't need right now. Okay. Don't need that one either. Okay. So I'm going to do a couple simple examples of, first of all, getting equilibrium solutions, and then understanding how a solution behaves for the non-equilibrium case. Now, a very simple DE that we've seen before, for modeling, for instance, population growth, dy dt is equal to constant r times y, and then we have initial condition. And for this example, we're going to assume that the constant r is positive. Okay. Now, I have shown you how to solve this, the solution is exponential, but that's beside the point right now. So we need to look at this right-hand side, see for what values of y is this equal to 0, and that's the equilibrium solution. So what's the one and only equilibrium solution in this case?
0.
Yeah, y not equal to 0. Okay, so now what I'm going to do is, draw not just the ty plane, but off to the side, I'm going to draw a real number line vertically, and I'm going to call it the phase line, or it might be called the phase portrait. It's called phase something. But you're going to see this in the homework, exactly as I draw it here. So when you pick out an equilibrium solution, mark it on this phase line. However many you have, mark them like in order, like you're marking a real number line. I know we're accustomed to it being horizontal, but in this case it's vertical. Okay, in this case we have only one, but next example of more than one. And so here we have a constant solution. So then what you do is you check values of y on either side, so in this case positive and negative, and find out is dy dt positive or negative in those cases. So we consider y naught being positive and negative. So what you can do, you can always pick a value that's positive, just plug it in, get the actual number, see if it's positive or negative. Or you can just, by inspection, see if it's going to be positive or negative. So when my initial value is positive in this case, dy dt, is it going to be positive or negative? It's going to be positive because y is positive and r is positive. You need to consider both. Okay, and if y naught is negative, it's going to be negative. Once you determine positive or negative, we indicate this on the phase line. So by putting an arrow going in this direction for positive, and in this direction for negative. So this gives us an idea of how solutions are behaving with respect to an equilibrium solution when y naught goes away from that equilibrium value. Now, what we see in this case, the arrows in both cases are going away from the equilibrium point. What that would mean is a solution behave, if I choose y naught down here, say like at 1 for instance, solution is going to go like this. If I choose y naught down here, a negative value, dy dt will be negative, solution is going to behave like this. So aside from this one equilibrium solution, if I choose any other initial value, the solution will diverge away from that equilibrium solution. So this is a sign that the equilibrium point is unstable. So when you have both arrows going away from equilibrium on your phase line, we say that it's unstable. Now, to tweak this example a little bit, what if the constant r is negative? What would happen to my phase line in that case?
Switch.
Yeah, it's going to be the opposite case. So the signs will be different. So if y naught is positive, y prime is negative, y naught is negative, y prime is positive. So your phase line in this case, so I mark 0, and I get this situation. So solutions are converging towards this equilibrium line. So if I draw my ty plane, solutions are behaving like that instead. So this is a stable equilibrium. All right. So arrows going away, unstable. Arrows going towards, stable. Now, what have I not covered? Is it possible to have one or the other, like one going towards, one going away? So I'll draw that situation real quick. So if this had happened, in other words, dy dt on both sides of the equilibrium should not be the same sign. So both positive, like I drew here, or both negative. So that would mean that if I choose positive initial data, it'll go away from the equilibrium solution. If I choose negative initial data, it'll go towards it. Which seems like rather odd behavior, but yes, it can happen. And this is called semi-stable. So that's how we understand the behavior of solutions of autonomous DE. If we're able to find the roots of f of y, so that we have however many equilibrium solutions exist, then we examine how dy dt behaves on either side of those equilibrium solutions and see how the arrows go. And let's classify each one. Stable, so stable, unstable, then semi-stable. Hopefully my gestures were helpful. Okay. Questions at this point? I will do more examples. Because this example, not very interesting because there's only one equilibrium solution. Now, this is an important ODE in the real world logistic equation. So y prime is equal to some constant r times y times 1 minus y over k. What? Okay, and then same old initial condition. Okay. So what we want to do is figure out when this right-hand side is equal to 0. In this case, it's convenient that it's already written in factored form. If it was not, then you would need to factor it. So for what values of y is this equal to 0?
0.
Yeah, certainly for this factor right here. And what's the other one?
K.
Yeah. Okay. And these are the assumption R and K are both positive in this case. All right. So we have two equilibrium solutions. So for our phase line, I'll mark 0 down here, and K is positive. I need that assumption so I know where to put K on my phase line, right there. So now we have 3 intervals to consider. So we have y not being negative, so way down there, and then we have y not being greater than 0 but less than k, and then we have y not greater than k. Now, suppose I'd given a specific value for k, like 5. Then you could plug specific numbers. You put any negative number down here. I could put something between 0 and 5 in here, something greater than 5 here. But I want you to also be able to look at the expression by inspection and determine if it's going to be positive or negative without going through motions of plugging some numbers in, especially if you need to use your calculator, because that just takes more time. So that's why I'm deliberately not giving a specific value for k in this case. R we can forget about, because R being positive is not going to affect the sign. So that's another thing is, again, you can do by inspection. You can figure out the sign of y prime just by looking at this part here. You can ignore the R because it's positive. If R was given to be negative, then you can still go ahead and figure out the sign of this part and just know to flip it. Right. So for example, suppose the initial value is negative. Then this factor y is certainly negative. But what about this one right here? We have 1 minus y over k. So based on k being positive, y being negative, what is the sign of this factor right here? All right, so if y naught is negative, k is positive, what's the sign of that whole expression going to be? It's going to be positive because we have a negative and a negative making a positive. So that is going to be positive. Therefore, what can we say about y prime as a whole? Positive or negative?
Positive.
What?
Is it positive?
It's actually going to be negative.
R is negative?
The whole thing is negative.
Or the whole-
Yeah, so R is positive, this factor is positive, but the y sitting here makes it all negative. So, all right, so then we have an arrow going in that direction. Okay. All right. Now, if we go here, y naught is in between. So this factor y is going to be positive now. But then we look at 1 minus y naught over k. Now, in this case, y naught and k are both positive. This fraction, therefore, is positive. But we're subtracting that from 1. The question is what we're subtracting going to be so large that it will make the whole thing negative, or will it remain positive? And this is where you take into account that y naught is not only positive, but it's also less than k. So this expression here, is that going to be, it's going to be positive. So because y naught is strictly less than k, y naught over k will be less than 1. What you're subtracting off is not large enough to overwhelm it. So that is still positive. So what can we say about y prime as a whole?
Positive.
It's going to be positive. Every factor now is positive. Okay. So we have an arrow there that covers this whole region between 0 and k. Can we make any conclusion about stable or unstable or semi-stable about any equilibrium right now?
Unstable.
What?
Is it unstable?
Yeah, 0 is unstable because both the arrows are going away from 0. We do not yet know about k because we have one more case to consider. However, between stable, unstable, semi-stable for k, is there any one of those that we can rule out right now?
You can rule out unstable. It has to be stable, semi-stable, right?
Yeah, because unstable would mean both arrows going away, but one arrow is already going towards. So now we just need to look at this situation here and find out which way that arrow is going, and that will tell us stable versus semi-stable. So y naught is now greater than k. So then we have, because y naught being greater than k, what happens to that expression right there?
Negative.
It's going to be negative now because y naught being greater than k, this fraction greater than 1, so what we're subtracting more than offsets for 1 to make the whole thing negative. Okay, so that factor is negative, so what about the whole thing? Y prime.
Negative.
It's going to be negative because this factor we determined was negative, but y and r are positive, so the whole thing is negative. So the equilibrium at y naught equals k is what?
Stable.
It is stable. Because both arrows are going towards k. All right, so we end up having one unstable equilibrium point and one that is stable. So if I were to attempt to draw solutions, so here's the equilibrium at 0, here's the equilibrium k, where the solution is a constant. If I choose initial value down here, it'll go away from an equilibrium. Here it'll go towards equilibrium. What happens in this case too, it goes away from 0. So even if I start something way down here as close to 0, it will not go towards y equals 0. It will go up towards y equals k. So that equilibrium line y equals k is it's like pulling solutions toward it like a tractor beam. So no matter how close you are to 0, it'll go up here. So that's what it means to be an unstable fixed point or equilibrium solution. Okay. So questions about how we yes.
If it was going all towards 0, it would be unstable.
Wait, if I mean like these solutions right here?
Yeah, they were all going.
Okay, so if I had something anywhere in this range going towards 0, and if nothing else changed, then 0 would now become semi-stable because the solutions are approaching it on one side but not the other. Y equals k would also be semi-stable because solutions here are going towards it, solutions here are going away from it.
So there wouldn't be a case where that would be Unstable. Where the whole solution would be unstable.
Here at K?
Yeah.
Well, actually, the easiest way to create that situation is I flip the sign of R.
Okay.
So if I make R negative, all these arrows will flip. So that would cause 0 to be stable and K to be unstable.
Okay.
Now, neither example that I've shown you has a semi-stable solution in it. Now I can tell you how to spot one before you even actually start figuring out this phase line. So if f of y has no repeated roots, then all the equilibria are going to be stable or unstable. In other words, semi-stable is not possible. So what I mean by repeated root, well actually I'll just make up an example that has a repeated root so you can see the contrast. So y prime is equal to y minus 1, the whole thing squared. Okay. So in this case, the equilibrium solution is, there's only one. Y naught is equal to 1. That's one only root. But because this quantity is squared, I can say that is a double root. Okay. So the multiplicity of a root would be how many times it appears in the factorization. If this was y minus 1 cubed, that would be a triple root, etc. So we go ahead and make our phase line, and I mark y equals 1. And so I want to know if dy dt is going to be positive or negative. But I don't have to go through anything like that. You can just look at it. So it's going to be positive or negative.
Positive.
It's going to be positive because it's something squared. That's the key. Always going to be, at least not negative. It's going to be 0 at 1, but anywhere else, positive. So go ahead and put your arrows. And sure enough, it is semi-stable. Okay. Now, if I had this being a triple root, when you take something cubed, that can still be positive or negative. So if it had been y minus 1 cubed, stable or unstable?
Unstable.
It would be unstable because y minus 1 cubed up here would still be positive, but this would now go negative, both arrows going away. If it had been y minus 1 to the 4th, both arrows positive again because semi-stable. So really, if you have a root of even multiplicity, y minus 1 or y minus y naught squared or 4 pi raised to an even power, that's where you have a possibility of having a semi-stable equilibrium. But if you take your f of y that's not already factored, it's given to you, you go ahead and factor it, you see, okay, there are these distinct roots, your equilibrium solutions, I guarantee they're not going to be a semi-stable one among them. They're all going to be, it's going to go alternate between stable and unstable. Just because between these equilibria, y prime will go back and forth alternate between positive and negative. And that's what leads to that kind of classification. All right. So questions about this example? Okay. While we're doing well on time, are there questions about homework? Still make it too easy? Okay. Well, I gotta check. The first test will be 3 weeks from Wednesday. So what I'll be doing is sometime next week I'll be composing the real test, but also practice test. I'll get that put aside. So in this section, certainly you can expect let's see, questions involving like interpreting a direction field or matching a direction field of an equation like on the homework, or given a DE like this one, find equilibrium solutions, draw your phase line, classify them as stable, unstable, semi-stable. Okay. All right. And the first assignments for Chapter 2 are already up. I'll be putting more. Okay, what I will do now, at least get started on what the focus of this chapter will be, and that is actually coming up with explicit solutions for these kind of equations. And I'll be showing you a number of different techniques where you have to, so the first task when you're given one of these equations is, okay, which basket does this fall into? Is this a separable equation? Is it linear? Is it homogeneous, etc.? But really, all of these techniques, though they appear to be very different, are closely related. So I'm going to give you an idea as to how these solution techniques come about in the first place. Because the solution depending on the equation at hand, might be explicit, meaning that your final answer is of this form, y of t equals something. So, which is convenient because then you can just go ahead and plug in any value of t and get the corresponding y value. The other possibility is implicit. So instead of having y equals something, you might have some function and the capital F, so it's not the same as this little f down here. I'll be sure to make that clear when I write them. Of t and y is equal to 0. So you have an equation that describes y implicitly as a function of t. So some simple examples of both, like for example, y of t is equal to t squared. You just plug in a value of t, you get the y. Here we have y squared plus t squared is equal to 1. Or actually, I'll write it this way. Y squared plus t squared minus 1 is equal to 0. Now, yes, you can, in many cases like this one, take this equation, rearrange it, and isolate y. But if I do that in this case, what ambiguity comes about when I have tried to rearrange that and just solve for y? You have a square root. So I can isolate y squared, no problem. But then I take a square root, I have y is equal to plus or minus something. So in other words, because this solution, what's the graph of this? It's a unit circle. So this unit circle, I cannot describe entirely by y as a function of t. It is not a function. It fails what you know of as the vertical line test. So I draw a vertical line, it passes through 2 points. So that's why sometimes we have to settle for a solution in this form, f of ty is equal to 0. And in some cases, that's all the problem will ask for. You're allowed to stop at that point. Some problems, like in the homework, they will say, find an explicit solution, y to equals. In that case, you got to go all the way and solve for y. So pay attention to the wording of a problem in that case. I may also use that on a test, where in some cases, I really do want an explicit solution. Other times, I'm fine with leaving it like that. Okay. Now, I'm going to work with this one to give some insights to how solution techniques, for whatever kind of problem we have, can come about. So I'm going to take this equation here and differentiate both sides with respect to t, keeping in mind that y is assumed to be a function of t. So what do I get? I get partial derivative of f with respect to t. So in that case, you're just differentiating with respect to t, you're thinking of y as a constant, plus derivative of f with respect to y, but y depends on t, so I have to use the chain rule, dy dt, and the right side will be 0. So if I have any kind of implicit solution, then it has to satisfy this. Now, what I'd like to do is have this match my original equation. So I can go ahead and rearrange this and solve for y prime, dy dt. And what I would get, I would just move this to the other side. So minus df dt, and then divide by df dy. And that is supposed to equal little f of ty. So you can say that the goal is to find capital F as a function of 2 variables, t and y, such that minus df dt, I'll use this notation of what is partial derivatives. The subscript indicates which variable you're differentiating with respect to. So minus ft over fy is equal to little f of ty. So if I can do that, I'm done. I've solved the equation. I can just write down what this f is, and I have my solution, at least implicitly. And then, if a function capital F is of a nice enough form, maybe I can rearrange it, solve for y explicitly as a function of t. But this is pretty hard to do. Unless the equation involved is trivial, you can't normally expect to easily find a function capital F that will satisfy that. So what we're going to do is try to get the equation in a form where this can be done. Because what I can always do to any equation, any kind of equation, I'm allowed to perform operations on both sides of it. I can multiply something, multiply both sides by something. I can add something to both sides. I could do any of those things that will make the equation simpler. Okay. So now, what I'll do first, I'll take my original problem, and so this is my original problem. I've just moved everything onto one side. See, everything I've done here, I always have equal 0 on the right-hand side. Now, I will multiply both sides, bless you, times some function mu of both t and y. Okay. Now, so now we match this against what an implicit solution would satisfy. What I have over there. df dt plus df dy, dy dt is equal to 0. And a lot of solution approaches like this come from just taking seemingly independent equations and matching them with one another. These equations have the same form. They both have a dy dt in this second term. So I can match these two. I can match these two. Because capital F is something I'm trying to find. So I get the following. df dt must be equal to minus mu little f, and capital F dy must be equal to mu. Now, right now, little f is the only thing that's set in stone. That's the only thing that's given. Now, the next thing I can do to try to narrow down what mu should be so I figure out what capital F is, I can differentiate both sides of these. I'm going to take the first equation and take the derivative with respect to y. So it's already differentiated with respect to t. Now I differentiate with respect to y also. So this is the same thing as second derivative of capital F with respect to t and y. This is a shorthand for it. Now on the right side, I have a product. I'm differentiating with respect to y also. I have to use the product rule. So I get minus mu y f plus mu f y. Okay. Then I take the other equation, differentiate both sides of it with respect to t. F y t is equal to d mu dt. Now we're getting somewhere, believe it or not, because if I take a function and differentiate it with respect to the same variables, here differentiate with respect to t and y, here differentiate with respect to y and t, the order doesn't matter. The result is the same. So in other words, these are equal. So I can say that these are equal. And the nice thing about this is capital F is now out of the picture. I only have one thing to look for, because little f is given. I need to find a function mu that will satisfy that. And So the term mu, because I used it to scale the equation, is called an integrating factor. So pretty much any approach I will show you for solving different kinds of first order ODEs reduces to this: finding the right kind of integrating factor that satisfies this and therefore makes actual solution possible. Now, how we go about solving this, finding a mu that satisfies that depends on the DE you're given. For example, you might make some assumptions. For example, if I can assume that mu is a function of only y, then mu t is equal to 0. Now we'll simplify things. Or it might go the other way. Maybe you assume mu is a function of only t. And in fact, we will make both kinds of assumptions in different situations. Okay. Now, and I will show you how to do that in different situations. But once you do find it, your solution is described by capital F. That's what you need in the end. But what I can do is I can go back to here. I can take this equation, df dy is equal to mu, and I can integrate both sides with respect to y. So I can say that capital F of ty is the integral of mu of ty with respect to just y. So it may be a function of both t and y, but you treat t as a constant, and you use your Cal2 integration techniques on this, focusing only on the y variable. And once you do that, you'll get a function that I'll call capital G of ty, which is the antiderivative. But when I work out that integral, I need to include what? Plus c. But plus c is going to be a little different this time, because this function depends on both variables t and y. If I integrate with respect to y only, then what I add on to it is not a constant, it's a function of t. So, because now if I take a derivative of both sides of this with respect to y, this would still give me 0, and I'd be back to this. So you have to keep it in mind, when you're dealing functions of more than one variable, when you take an integral, you're not adding on a constant, you're adding on something that doesn't depend on the variable you just integrated with respect to. I integrate with respect to y, I add on something that does not depend on y, but it can depend on anything else. Okay. And at this point, if mu is found, everything here is known, except this constant of integration that isn't really a constant. But that's okay, because so far I've only used this equation. I still haven't used this one. So what I can do is I can differentiate both sides of this with respect to. So now df dt is equal to derivative of this with respect to t plus c prime of t. And that has to be equal to minus mu times f. So everything here is known except for c prime. But now I can solve that. And once that's done, capital F is known. I set it equal to 0, and I have my solution. If I have an initial condition, when I solve this, there will be an actual plus c, a constant involved. That would help satisfy my initial condition. So all I'm showing you here is a framework of sorts, just to indicate that even though I'm going to be showing you a bunch of different things you might consider these techniques to be completely separate. They're really all stemming from the same idea, and that is we're trying to find a solution that fits this form, and whether the solution can be explicit or implicit, it can always be written in this form, just not necessarily in this one. And bless you. So if we can just find this, then we're done. And that has been reduced to, like, because first I characterized it this way, and this was actually not helpful. But now the problem boils down to finding a function mu that satisfies this for the f that we have. Okay. So what will happen on Wednesday is we'll consider the first type of first order equations that will solve first classification, that is equations that are separable, where f can be written as a function of t times a function of y. And what happens in that case is we can make an assumption on mu that it depends only on y, not t. Therefore, this right side becomes 0. And then we'll be able to very quickly solve the equation from there. So once we have this, we just go for this. And so it's sort of like a unified procedure for solving all these equations. I realize it's not very concrete right now, but just to set the stage for everything that we'll see in this chapter. Okay, so I will start with separable equations on Wednesday. I'll stick around in case anyone has any homework questions.